the invitation and also thank you for inviting me. I'm really happy to have this opportunity to discuss my work. As Mark was saying, I'm a PhD student at the Niels Bohr Institute and the University of Copenhagen. And I'm also a member of the quantum gravity group that is led by Professor Alessia Platania. And today I'm going to talk about a work that I've done in collaboration with her and with postdoc Francesco del Porro. And so the title of the presentation is Impact of Quantum Gravity on the UV Sensitivity of Extremal Black Holes. And there are two main concepts that I wanted to unpack in this title, going through it. The first one being quantum gravity, and the second one being the UV sensitivity of extremal black holes. Now, as for quantum gravity, I hope it's not, okay, it's not, okay. I hope it's not surprising that what we worked on, what we focused on, is asymptotically safe quantum gravity. Now, I don't know if some people may not, or maybe are not familiar. They are outside from the field, so I just thought I'd give a very brief introduction as to what it is, and like very briefly. Now, ASQG is a quantum field theory-based approach to gravity, to quantum gravity, that is treating gravity as a consistent QFT at every scale. And the idea is based on the fact that your UV theory is controlled by an interacting fixed point of your couplings. And so essentially, this framework has proven extremely successful in many regards. And there is not a proof, but there are many indications hinting towards non-perturbative renormalizability. But then also in the case of gravity coupled with matter. And especially, okay, hold on, this is, okay, in the case of gravity coupled with matter. And this is, for example, for the top to Higgs mass ratio, but even other standard model parameters. And I wanted to stress this because this is actually, because even if asymptotic safety were not to be realized at a fundamental level, there is still room for it. And in the sense that it can still be realized as an effective realization of something more fundamental, say, take whatever your favorite approach to quantum gravity, say, for example, string theory, and asymptotic safety could be realized at an effective level. And I wanted to stress this because this is actually going to be rather central for the purpose of my talk. And now, by definition, ASQG is actually built upon the Wilsonian renormalization group approach. And so, as such, it actually offers a very clear recipe for computing Wilson coefficients. So, essentially, the idea is you have your UV theory, which is governed by your non-interacting interacting fixed point, and the idea is you simply follow the flow stemming from the UV of all asymptotically safe trajectories, and then you simply identify your Wilson coefficients with the infrared limits of your FRG running couplings. So essentially, just to be more concrete, you have your infrared running couplings of your asymptotically safe trajectories, and you study the K to 0 limit. Now, this was just a very, very brief introduction to ASQG, but actually the second concept is more central for this talk, which is the UV sensitivity of extremal black holes. And this is essentially because our work builds upon a PRL that was published 2 years ago by Horowitz and collaborators. And what they did is they considered Einstein-Hilbert gravity in the presence of higher curvature terms. And specifically, what they showed is that if you consider this theory, so if you have this theory and you study the equations of motion, you have that the maximally rotating solution to these field equations actually exhibit divergent tidal forces on the horizon. Now, I thought just to be more concrete, they work within this NEFT scenario. So you essentially expect there to be higher derivative operators of any order. But what they do is they consider Einstein-Hilbert plus higher derivative operators. For the purpose of my talk, actually, it's enough that to stop at just truncation here, so up to 6 derivatives. And so they work within the essential scheme. And this is, mind you, this is in vacuum. So essentially, you have no 4 derivative operators because you can actually map all the operators to the Gauss-Bonnet term, which is topological, and so by definition, it doesn't affect the equations of motion. And this is exactly what interests them. And so what you're left with, essentially up to 6 derivatives, is this Gorodov-Zagnati counter term, where eta is your Wilson coefficient. So essentially you have this Riemann cubed operator. And this is historically, even historically speaking, it's very relevant because this was actually what showed that gravity is perturbatively non-normalizable. And so essentially they consider this theory, and then they say, okay, let me study the equations of motion stemming from this theory, and specifically let me focus on the extremal Kerr, the case of the extremal Kerr. So in particular, the FT corrected extremal Kerr. And what they do in more detail is they consider the near horizon geometry of extremal Kerr, where this is actually, you can exploit the fact that you have an O2 1 times U1 symmetry, and so essentially you can actually have an expression for your near horizon geometry, and then so you have this near horizon geometry, and then if you want to connect it to the asymptotically flat region, this is actually giving rise to external deformations. And so essentially what you can do then is you study the response to these stationary and axisymmetric perturbations if you restrict your analysis to them. And then so essentially then you study your curvature invariance and whatnot. And specifically, you can study what they do is they study the Val tensor. And specifically, they show that a specific component of your Val tensor is actually exhibiting a power law behavior in rho. Now, rho is a coordinate that actually goes to 0 on the horizon. It actually is the affine distance from the horizon, and so essentially you're reaching as you're reaching the horizon, rho goes to 0, and so you have this actually power law behavior, which is actually a remnant of the fact that you have this ADS2 geometry, and in the near horizon, obviously. And so you have this behavior for the Weil tensor, and this is actually flagging a potentially pathological situation. It's pretty straightforward to understand this. Essentially, you have a power law behavior with an exponent that goes as gamma minus 2. And so, okay, say you turn this off. Say you turn off the Gorodov-Zagnati counter term, then gamma minus 2 is simply 2 minus 2, so it's 0. And so essentially for the case of extremal Kerr, so no EFT corrections, just Einstein gravity, the horizon is perfectly smooth, everything is working perfectly fine. But then you say, okay, well, let me turn this on. Let me consider let me turn on my higher derivative correction, and let's see what happens. And specifically, when I say let's see what happens, essentially you have this correction to your gamma exponent, and this correction here is dependent on the Wilson coefficient. Now, gamma 6 is actually a parameter that is fixed by the theory, and specifically, it is actually written in terms of the spin of your black hole, the dimension of the space-time, and so forth. But what is relevant for us is that it's bigger than 0. Whereas on the other side, you have eta. And so essentially, you can immediately understand this as, okay, I have something that goes as rho to some power, where the power is 2 minus 2 plus eta gamma 6. And so essentially, if you have eta that is smaller than 0, well, then this is actually, this is pathological, because this is actually because then the Weil tensor is going as 1 over rho to some power, which is bigger than 0. And so essentially, this diverges as you're reaching the horizon. And this is exactly what I mean by when I say that there are divergent tidal forces, because essentially you can just connect them to the Ricciardo equation, and you have this divergent component of the Weil tensor. And this is extremely surprising in many ways. And for example, there is the fact that the scalar curvature invariants at the same time actually remain finite, even though you have these tidal divergences. And but at the same level, you also have that the horizon is actually uniquely sensitive to UV physics, and specifically because you have that the fate of your horizon is very dependent. It's really contingent upon the sign of your Wilson coefficient that is determined by your UV. And so now I hope you kind of have a clear idea of where this is going, I hope. So you have this framework on one side, you have this framework, which is ASQG, which is offering you a very clear recipe for computing Wilson coefficients. And on the other side, you have this fate of EFT-corrected Kerr black holes that is really contingent upon the sign of your Wilson coefficients. And so essentially the idea of our work was, okay, well, let's see what ASQG is predicting for us. And specifically, what we did is not start with this action as a starting point. So not the Riemann cubed operator, but actually rather this equivalent basis here, where you have the Val cubed operator. And now this is not a problematic in any way, because essentially, as I was saying, you're working in the essential scheme, and you can actually map the Riemann cubed operator to the Val cubed operator just simply via local Fourier definitions. So Fourier definitions involving the metric and its derivatives. And since this is involving local Fourier definitions, actually you are leaving the equations of motion unaffected. And so if you're leaving the equations of motion unaffected, then this actually means that you can translate the problem within this section here to this here. It's a one-to-one correspondence. And so essentially you can immediately see that you have a divergence if this coupling here, which I'm going to call from now on the Gorov-Sagnotti coupling, is actually smaller than 0. And so this is just a one-to-one translation. And so essentially, the idea then is, okay, if I want to get a prediction for my coupling, I solve for the beta functions, and then I study the RG flow, and in particular, I consider the infrared limit of all asymptotically safe trajectories. Now, there is a reason why we consider this equivalent basis. And the reason is the fact that actually the beta functions are already there in the literature. And specifically, we took them from this paper by Baldazzi, Falls, Kluth, and Knorr. And so essentially, we already had this the beta functions, and we could immediately solve for the RG flow and then study the infrared limit. And so this is exactly what we did. Now, sorry, but this is, let me hide this. And this is exactly what we did. So essentially, we studied the flow of all dimensionless couplings. So in this case, our dimensionless Gorov-Sagnotti coupling and our dimensionless Newton coupling. And then you study the flow, and then you focus on the k to 0 limit. Now, actually, there is a result in the literature quite a few years ago now, which is essentially already showed the fact that if you work within this truncation, the UV is actually there's two fixed points, so there's also one non-Gaussian fixed point, and also the Gorov-Sagnotti coupling is irrelevant. Now, this was extremely relevant in the field because this actually showed that the two-loop counter term was not problematic; it was irrelevant. And but for this case here, the fact that you've only got one relevant direction, it tells us there is only one unique trajectory that is connecting your UV to your IR. And essentially, what this means is that you have no free parameters after fixing the scale. And because the idea is, if you have n relevant directions, then the number of couplings that you need to fix by experiments is n minus 1, because you need to fix the scale. And so in this case, we have only one relevant direction, and so we have a zero parameter theory. And so essentially, ASQG can uniquely determine the fate of your horizon within this truncation. And so the idea is then, okay, let me consider this asymptotically safe trajectory. So this is actually a zooming in of this of the trajectory, and let me then study the k to 0 limit, and then I can identify the Wilson coefficients as the infrared limit of my FRG running couplings. What I mean by this, to be more concrete, is the fact that I can immediately find an expression for my Gorov-Sagnotti coupling in units of Planck mass, simply as this ratio here. So you have essentially you can translate this ratio here to this, because they have the same mass dimension. And so essentially what you can simply identify your Gorov-Sagnotti coupling by studying this ratio here in the k to 0 limit. Now, I wanted to zoom in on this plot, because actually there is one thing about the beta functions that is rather peculiar, and that I wanted to stress. That is the fact that actually, if you look here, the Newton coupling, the coordinate of the fixed point is 0 for the Newton dimensionless coupling, but it's non-zero for the Goddard-Sagnotti coupling. And so essentially, you have what I still call a Gaussian fixed point, because essentially you have that the couplings still follow the canonical mass dimension scaling behavior, but the fixed point is shifted. So it is non-canonical in the sense that your coordinates are not all 0. And now this is actually something that I wanted to stress, because this is actually really relevant even now as we talk. Because if you then focus on your infrared limit, you can immediately make an ansatz for your FRG running couplings. And I will discuss this later. But I wanted to stress the consequence, what this implies, the presence of this shifted Gaussian fixed point. And you can understand this pretty straightforwardly, because as you set k to 0, you have a value that is non-zero for your Goddard-Sagnotti counter term, for your Goddard-Sagnotti coupling. Whereas the Newton dimensionless Newton is simply scaling as a power law. Now, the reason why I wanted to stress this is the fact that if you get back to your ratio, so your ratio between your dimensionless couplings, essentially you can immediately understand how this is displaying 1 over k squared behavior. So it's actually diverging in the limit k going to 0, because here you have this constant, and so you have this constant plus other stuff, and here you have k squared. And so essentially you have a piece that is going as 1 over k squared. And now this is actually something rather peculiar, and I wanted to discuss its physical implications, because then one could immediately raise the question, well, what about this 1 over k squared behavior? Is this a physical or an unphysical behavior? And because if you actually approximate k running with p running, we know that this is not exactly true, but if you work within this approximation, well, then actually this 1 over k squared behavior is telling you that there is an infrared non-locality, because this is actually going as 1 over box. And so essentially you have this infrared non-locality, which in some sense, this is something that had been found already in the literature. For example, for a non-local term of in this reference here. But then the question is, if this is an infrared non-locality that has a physical meaning, then the question could be, could we have already found this, observed this within, or are there observational bounds? Now, I will not talk about this further, because this is actually not the scope of the presentation. But essentially, if you actually work within this 1 over box term, you can actually see that, first of all, there's this work that is telling you that if you study the Bekenstein-Hawking radiation, so if you have only Einstein gravity, you have the Bekenstein-Hawking or the entropy, sorry, not the entropy. And then you say, okay, let me consider the contribution coming from higher curvature operators. But then there is this work where you study the contribution coming from a non-local term, and where they find that actually the entropy seems to be divergent, if not highly fine-tuned. And also, there's also this discussion, this very interesting paper, where there's this discussion about holography and even just black hole thermodynamics in QFT, and it seems to be disfavoring in QFT. And actually, the presence of this IR non-locality would actually be a loophole in the whole discussion. And so this is actually some ideas about this 1 over k squared behavior, but actually we were not entirely sure about this. And indeed, we talked with Benjamin Knorr, especially because he was one of the authors for the beta functions, and he was saying that it could be that it's actually tracing it back to the regularization that they used in computing the beta functions. And so specifically, he was saying that actually it could be that actually this is because the regulator is non-natural in the sense of a paper that he wrote. But if you want, we can discuss this later. And so essentially you have this non-Gaussian, this shifted Gaussian fixed point because of this. And so now, if this is actually unphysical, as this would point towards, essentially there are two ways that you can actually go about, and that we actually went through. One of them is, okay, I have a possible prescription for defining the Wilson coefficients. That is, instead of focusing on the ratio of my dimensionless couplings, I just focus on the ratio of the deviations from the fixed point values. So essentially, what I do here naively is I'm subtracting the divergent part by hand. So, because essentially, I mean, this can be understood as I'm focusing on the infrared behavior close to the fixed point, but still this is an ad hoc procedure, if you want. On the other side, you could say, okay, well, then I can adopt a regularization with natural endomorphisms. And indeed, we asked Knorr if he could give us, if you could provide us a modified version of the beta functions by changing a parameter of their flow, and he was so kind to do that to us for us, and essentially he gave us this modified version of the beta functions, where indeed the Gaussian fixed point is not shifted. So indeed, so as I was saying, you can just you can do both things. You can study this the value of this Wilson coefficient. You can get it in these two ways, and I'm going to talk about both actually. And first, I'm going to focus on this naive subtraction, if you want, of the divergent part. And so now finally I can get back to this expression here that I was discussing about earlier. And so if you actually focus on this ratio here, essentially you find, and then you study the k to 0 limit, you find that there is a logarithmic running. And indeed, you can understand this because this is actually scaling linearly in the RG time, t. And so essentially you have that your Garoff-Zaniotti coupling is running logarithmically. And now, mind you, this is not a marginal coupling. This is actually, but there's still a logarithmic running nonetheless. And this is actually induced by the integration of massless fluctuations. I'm going to talk about this in a second. But essentially, you can also relate this to the presence of logarithmic form factors in the quantum effective action. So essentially, you have form factors of this form here, where you have the box operator, and then you have a transition scale, lambda qg, which is essentially setting your energy, your characteristic energy for the qg regime. Now, as for this logarithmic running, this is an open problem in effective field theory, in the sense that there is an ambiguity in the definition of Wilson coefficients in the presence of these massless fluctuations, where now obviously our massless fluctuations are the graviton. So, and indeed, there's this logarithmic running if you consider the scattering amplitudes, or even there's this ambiguity even when you study positivity bounds. And but then if you just take a step back and then you start and you think about our starting point, which was the action by Horowitz and collaborators, the action was written as such. So it was a local EFT. So essentially just considering the constant part of your Wilson coefficient so neglecting all logarithmic form factors in your quantum effective action. So you've only got this constant part. So the fact that you've only got this constant part means that, okay, well, if you want to give a prediction for this, if you want to translate this, and okay, then you have to decouple the logarithmic running from the constant part of your Wilson coefficient. And so essentially you need to identify the constant part, and this will be the one entering here. Now, the fact that you have this this logarithmic running, though, is actually introducing an ambiguity. And you can immediately understand this, because if you actually say change the value of k naught, so say you have k naught and then you consider k naught times a factor, well, then simply by logarithmic properties, this is simply telling you that this is shifted. You're shifting your constant part. And so essentially you need to fix k naught, which is now going to be our transition scale. And so if you want to get a unique prediction for your constant part of your Wilson coefficient, and so essentially you need to fix your value of k naught. And if you work within a fundamental realization of ASQG, the choice for K naught is straightforward because you have that the Planck mass is the only scale that is naturally appearing in the system, and so essentially you can immediately make a connection and choose K naught as the Planck mass. And now, if you want, we can also discuss more in detail the what we did here. But the idea is you actually remove the logarithmic running in such a consistent way. So you actually have your ratio with your logarithmic running, and then you simply remove it consistently after you fixed K naught to be mass Planck. And if you do this, if you follow this whole machinery, essentially you find and then you study obviously and then you can translate this to your ratio for your Wilson coefficients appearing in the quantum effective action. You find that this ratio is bigger than zero. And I thought I'd put these here just to refresh the memory if you want. But so if you have this component of the Weyl tensor, you have that this is going as rho to some power, where the power is actually bigger than zero. So everything is perfectly fine, and essentially you are avoiding your divergence. Everything is perfectly regular. So at least this is in the scenario where you actually consider this ad hoc prescription, if you want, where you're removing your divergence. But then you say, okay, well then let me focus on the natural regularization scheme. Within this natural regularization scheme, as I was saying, you actually have a Gaussian fixed point, which is non-shifted. And now the two flows actually share the same UV physics. So you expect there to be the same qualitative behavior. And but now actually what you have is this ratio here. Now this ratio is well defined. And so essentially you can immediately translate this to this ratio. And so indeed you can just do the whole machinery all over again. And indeed you find that this ratio is scaling logarithmically. So your Gorovsky coupling is running logarithmically. And then so we're back to the discussion of a few minutes ago. So you need to fix K naught. And if you fix K naught to the Planck mass in the fundamental scenario of ASQG, again, you find a value for your Gorovsky coupling, which is bigger than zero. So consistently with the other result. Now, in total honesty, this result is actually orders of magnitude smaller than the other result. And now this is not this. We still need to understand better why. But actually, this is not really surprising because previously in the procedure that I told you about earlier, you were removing the divergence by hand, and also now you have that your infrared is governed by two different fixed points. But still, it is interesting to note how you get the same result for your Wilson coefficients. So you get the same results for the fate of your extremal Kerr black holes, EFT corrected Kerr black holes. And so then this is within a scenario of a fundamental ASQG. But then you could say, okay, well, what happens in a scenario of effective ASQG? What happens if I actually depart from the Planck mass and I go beyond this? So essentially, I consider a K naught, which is perfectly general. So if I consider a generic value of K naught, so something proportional to mass Planck, where Xi is is essentially telling you how big K naught is, what this actually tells you. And you can immediately understand this looking at the way that you're actually removing the logarithmic running once you set the scale. And because you're removing it with this subtraction here. And essentially then, if you actually consider a generic K naught with this Xi parameter multiplying, well, then it's straightforward to understand how actually this value at mass Planck is actually being shifted. So you have this value here, but then you have this sum here. And now, if you look at this, just look at this for a second. This is actually rather pathological, if you want, because so you have that this is bigger than zero. But then, well, what happens if this factor here is smaller than zero? Because if this factor here is smaller than zero, then you have a subtraction, and then a large enough value of your Xi is simply rendering your sum smaller than 0. So we're back to square one. And indeed, this is exactly what happens in our case. So we actually find that this factor here is smaller than 0, and because this is essentially you can get this, you can relate this to the slope of your line here, and so it's smaller than 0. And so the idea is, okay, well then let me change my point of view. So instead of let me actually demand regularity on the horizon, and let's see what this is actually implying. And it is just by looking at this, it's actually rather immediate to see that actually this is equivalent to setting a lower bound on your transition scale. So essentially, you have like K naught needs to be bigger than a lower bound. And indeed, if you you plug this in, you plug your value for your Wilson coefficient, you find that K naught you find that the lower bound is of order 10 to the minus 1 mass Planck. And this maybe I should have been more clear. I hope I was. All of this being within the scenario where you're actually considering the ratio of the deviations from the fixed point values. And so you actually have this lower bound. And so you say, does anybody want to say something? No. Okay. Sorry. And so you say, okay, well, this is obviously expected in a fundamental realization of ASQG. And okay, well, you could say, well, what are you telling me? This is not surprising in any way. You just had it computed earlier and you found everything regular. True. But then you say, okay, well, what happens if I consider a generic value of K naught? And say, for example, that that asymptotic safety is a low energy realization of string theory. Then its transition scale actually needs to lie below the string scale. Now, there are many general arguments in EFD that actually tell you that the string scale needs to be sub-Planckian. And if it needs to be sub-Planckian, then you see that there is very little room for this bound to hold, because the K naught needs to be smaller than the string scale, which is sub-Planckian, but at the same time, this bound needs to hold. And so essentially you can understand how there's very little room, and so the divergent tidal forces may very well reappear on the horizon within this scenario of effective asymptotic safety. And this is in the case where you're considering the ratio of your deviations. But actually, this is exactly the same result that you get within the natural regularization scheme. So essentially, you just perform the same analysis. And again, you have this value being shifted, and you find this lower bound. Again, actually, the lower bound is very similar to the other one. The result is consistent, but it is also a very similar result for your lower bound. Now, oh well, I really ran. I'm sorry about this, but I guess that this is actually I'm coming to the conclusions, and okay, then I guess there's a lot of time for questions. But essentially, you have that the authors of this paper, they were saying that in the presence of higher curvature terms, asymptotically flat extremal rotating black holes have curvature singularities on their horizon. And we actually show that this is not exactly true. We showed that within a fundamental realization of ASQG, this is not true, because actually this is predicting regular tidal forces on the horizon. And but at the same time, we showed that within an effective realization of ASQG, this does not actually necessarily need to hold, and tidal divergences may very well appear in both scenarios. So considering both the ratio, this case where you have this IR 1 over k squared divergence, and you say, okay, let me subtract it within an ad hoc procedure, and or within a different regularization scheme. And we found that we found these results to be consistent. And then just to change the point of view, first of all, I wanted to highlight this presence of this 1 over k squared divergence. And one may wonder if this is physical or if it's just a regularization artifact. Me personally, I don't know. I'm not sure. But I'm actually really looking forward to some questions or some discussion because I would like to have some feedback on this. And then also just changing the point of view, I wanted to discuss the logarithmic running. And indeed, if you one point of view could be, okay, I have this analysis within a local EFT where you're actually considering the constant part of your Wilson coefficients. It would be very interesting to see, okay, well, let me consider not a local QFT, not a local EFT, but actually let me repeat the analysis where now though you have logarithmic form factors in the quantum effective action. And this can be extremely interesting also comparing this to the prescription that we used. And yeah, I really ran, but this is all. And thank you for the attention. This is the code on archive if anybody's interested. But I guess that if you want, this is time for questions. And I've also got something more to say if you want.
A lot. Let's thank Francesco for the nice talk. And we do indeed have time for questions. So